Hey everyone. I'm just gonna hop right into Discord. Um, oh, you know what? Oh, I'm not even prepared. I thought I was prepared, and then I realized that I wasn't. Didn't even have my tablet out. Um, oh, I don't want that window to be open. I'm forgetting something else. Hey, Fembucks. You need to check if this thing is still going. Okay. Now I think I'm good. Okay. Um, so yeah, today's reading group is on the first part of chapter 4, 4.1 and 4.2. I assume Fevax will hop in once he's ready. Oops, I didn't mean to leave. What the hell? Shows him on push to talk. Okay, voice activity. Hey, Fembucks.
Hey, I'm here.
Awesome. So you got through 4.1 and only some of 4.2, you said?
Yeah, I was trying to skim through 4.2 just like an hour ago, and I realized the stuff at the end. I don't know. There was too much in it for me to get through today. That's all.
Yeah, I didn't understand it deeply. I just kind of looked to see what the tricks were and then kind of moved along. Some of the things they did in that
Okay.
section were a little crazy, though.
Yeah, I got through maybe the first 3 or 4 examples from that section. I think I got through the first 3 maybe.
Okay. Jed, congrats on the
But
first.
I was reading another book, so I sort of understand how to do the ones where you substitute for sine and cosine, the rational ones in
Okay.
sine and cosine. I've seen some of those. And I've seen the ones where you want to integrate from minus. You want to integrate along the real axis, and you do it like a semicircle.
Mm-hmm.
So I've seen something like that. So if we get those kind of problems, maybe I'll be okay.
Okay.
Yeah.
I don't remember which ones I chose, to be honest, so we'll see. But yeah, so the big idea of this is Cauchy residue theorem, that the integral around a closed contour is equal to 2 pi I times the sum of the residues of all the poles, or rather isolated singular points, which could also be, I guess, essential, not necessarily poles. Um, and so they gave us a convenient formula to calculate the residue if it is a pole using derivatives and based on the order of the pole. That's equation 4.1.7 on page 209.
I was using 4.1.10 a little bit. I found that really
Yeah,
helpful.
that's another one, right?
Yeah.
This one I
That
read
only works
early
for
last week, so I
a
don't remember
simple
this part
pole.
as well. Sorry, what?
That's only for a simple pole, it said.
Right. I remember being stuck on this part on how I should pronounce D with the tilde above it. I spent way too long just like thinking about that.
I said D tilde.
I guess so. Yeah, that's the reasonable thing.
Hmm.
Um And it gets a little bit weird when they talk about residues at infinity.
Yeah.
In general, like when we talk about poles at infinity too, it gets a little bit confusing. Hey, color cone. um, they do give a more convenient way of. They just kind of give a formula for finding the residue at infinity, which is limit as z goes to infinity of z times f of z. But only if f of infinity is 0, I guess. If it's not 0, though, I feel like they said that has to be a constant function or something. Like if f of infinity is some random number. Maybe I'm misremembering, but I feel like there's something special. If it's analytic and it's... I don't remember.
Yeah, I didn't understand 4113. I didn't really know how they got that.
I don't think I did either.
Let's see.
They do a change of variables,
Yeah, I
so
don't really quite get it.
the infinitely large circle becomes an infinitely small circle centered at 0. The right-hand side is the coefficient of t inverse in the expansion f of t, f of 1 over t squared near t equals 0. The left-hand side is coefficient of z inverse in the expansion f of z at infinity.
Oh, maybe the way to think of it is instead of z times f of z, maybe it would make more sense to think of it as f of z divided by 1 over z. Maybe that'll make more sense to me. Because then if z goes to infinity, that 1 over z on the bottom is going to 0, and it's kind of like you're dividing out the 0 again. Kind of like we do with rational functions. You know, if you've got a common factor on the top and the bottom and they both happen to be 0, you can cancel them out. So maybe that's kind of like that.
Maybe, yeah. I think I understand where they're coming from now with, like, it's just kind of a change of variables in the integral. Actually, no, I don't know where the z out front comes from, now that I think about it. It's the coefficient of z inverse. Oh, okay. I kind of understand it. Honestly, but I still don't feel very comfortable with actually finding the Laurent series of a function, which is kind of an issue for this. But if I understood that piece better, I think that's where the z comes from.
Hmm.
So every rational function has a property that the sum of the residues around the poles is equal to the residue at infinity.
Wow.
And I think it's not necessarily rational functions from what I'm reading. It's the important part is that it has only isolated points in the extended plane and it's analytic elsewhere. So I wonder if for any function that meets that criteria, if the same would be true. I think it would be.
Okay. Like if we threw a exponential on top or something.
Maybe, I mean, I wonder if only rational functions meet that criteria, to be honest, but The only Merrill function is C plus point infinity. Okay. So yeah, Clark was saying it only rational functions fit that criteria. Okay. Exponential function has an essential singularity at infinity. Okay. Uh, okay, and then they talk about winding numbers.
Yeah.
And I've heard of this. I've heard of them before. Hey, Ralph. But I got kind of stuck on this delta theta sub j thing because I think of delta theta as just any change in theta, but like it's only kind of whole, like it's still a closed contour. You have to start or you have to end where you start. So it's
Yeah.
not like it has to be a complete revolution. Like it can only be like 4 pi, 6 pi, I guess negative 2
Right.
pi or something like that.
Yeah, yeah. So I think the winding number has to be an integer, right?
Yeah.
That's what I came up with too. I because it took me a while to think about it, but I was like, wait a second, this can't just be any number, real number. This has to be an integer. Yeah. Okay. Unless they define winding numbers somehow on a non-closed contour, but that's not what they're doing there, right? They're saying it's a closed contour.
Yeah. And I thought it was kind of neat how the multi-valueness of log actually helps define that in the step right before that. Where it's like you're crossing the branch cut for log, that's helping you count the number of times you wind around.
Oh.
If an incomplete turn, then the integral is 0. Okay. Yeah, because it wouldn't be closed anymore, I guess. Well, wait. Okay. Stupid question, color code. If you did a complete revolution and then an incomplete revolution, wouldn't it would just count, you would still have one like winding number, right? Just the second incomplete one wouldn't count? Or would it still be 0? Okay, yeah, you count just the complete one. All right, and then they generalize the Cauchy residue theorem to include non-simple contours.
Yeah, yeah. And the only difference was you multiply every residue times its own winding number, right?
Yeah.
Yeah, okay.
I thought they had a pretty well chosen example for to like show that too with the kind of crazy loop inside a loop
Yeah.
thing.
Yeah, this was a good one. The first time I did it, I got it wrong, but then I did it more carefully and I got it right.
Nice. Uh oh yeah, but
This I
then
didn't quite I
yeah.
didn't understand this very last page of 4.1. This was the only part of 4.1 I felt like I didn't really get.
Yeah, I did not understand the connection at all. Think wizard 0 is in case your path to find over simply connected domain. The integral has to be 0. Okay, yeah, I think of it as like you're not actually enclosing an analytic point. What doesn't necessarily mean 0. I don't remember. No, the n pi over a. So what is n pi over a?
Yeah, all this n pi over a stuff is relating to the example we just did, which was an integral of 1 over x squared minus a squared or something. What did this integral do? Oh, 1 over z squared plus a squared we were trying to integrate.
Yeah. They say the empire array came more generally for any two closed curves C1 and C2. This seems way too general of statement.
Yeah, no, that's what I'm saying. When I first read that, I didn't understand it, but they're still inside example 4.18 at that point. They're still talking about that particular integral.
Okay.
It's just that you could break that contour into two different curves, I guess, and the difference between them has to be some multiple of pi over a, some integer multiple of pi over a. You can kind of see it from the line above, right? Not 4,117, but the line above where they calculate the actual integral. It's 2 pi I times the two residues times their winding numbers, but the residues were 1 over 2ai and negative 1 over 2ai. So when you factor that out, the 1 over 2ai, you just get pi over a times the difference of the winding numbers, right?
Interesting, yeah.
Yeah, so that capital N in 4,117 is the difference of the winding numbers between the two curves.
Okay.
I think that's the conclusion I came to.
That's probably it, yeah. So you could rewrite it as like one integral minus the other.
Yeah, exactly. And that's what they do on the next page. They write like integral C1 minus integral C2.
Oh, right. Hey, Properba. Hey, Sage.
But once you get down to, the next part there, they're talking about now a general function. So it's not the same example.
Okay.
It's a general function. So it seems fair. It says it's like 2 pi I times the sum of the residues times winding numbers. But then when they're talking about an inverse function and this capital phi, I didn't really know. I didn't follow what they were talking about.
Me neither.
The period inverse function, right? Because they were talking about like inverse tangent up above.
Mm-hmm.
Yeah, I didn't quite get all that.
Yeah, I'm trying to understand it now, and it's like, no, I still don't know what they're trying to get either.
Yeah, they're saying something's periodic.
And they're still talking about A, so it must be related to the same example.
Yeah, when they're talking about n pi over a, that's the same example. But then when they said like incorporating the winding numbers, blah blah blah, that's just more general, I think.
Yeah. So yeah, I'm not quite sure what to think about that.
We probably won't need to. We probably won't really need to know that.
Probably not. So yeah, that was the end of 4.1. 4.2. This entire section kind of reminded me of like going through Calc 2 for the first time and having to learn a million different tricks to integrate things, but with complex numbers.
Yeah, it's so cool, isn't it?
Yeah, it's kind of intimidating though.
The ones I did today, I was having so much fun with them. They were really cool.
Oh, nice. I was kicking myself so hard when I read the very first part of this, which is, I think I was talking to like Lucas about the type of integral of like 4.2.3. I was trying to make a point that like there's like a weird thing where the difference between 4.2.2 and 4.2.3 is that the last one comes out to 0, the first one comes out to like infinity minus infinity.
Yeah.
And I overlooked that, and I completely like next time I see Lucas, I need to go back and like correct that. But like I was trying to make a point about how like you get infinity minus infinity, and so you shouldn't like say certain things about cancellations, like the integral of like 1 over x from minus infinity to plus infinity. Like that's the situation where it comes up too.
Right.
And so I
Yep.
I only did the second thing. I was like, oh, I guess I was wrong, and it's just 0, but that wasn't quite right.
Yeah, it's weird, isn't it?
Zartan
It's
PhD
weird.
Enthusiasm. Yeah, oh yeah,
The
it
other
is
book,
weird.
the other book I was reading was talking about just y equals x, and they said, what if you want to integrate y equals x from minus infinity to infinity?
Mm-hmm.
And they said if you set it up the second way, like 4.2.3, you can make it 0. But if you set it up as 4.2.2, it's not defined or whatever, or it's not doesn't converge.
Yeah, and they interesting. Like this
Yeah.
book describes the second case as more restrictive, and I don't understand how it's restrictive rather than just different.
Oh, it's more restrictive because you don't have two things you can move, right? Instead of having a slider at L and a slider at R, you only have one slider and they've got to be symmetric. They've got to both go out at the
Oh,
same
okay.
the same. I think
Yeah.
that's why it's more restrictive. Yeah, because you're setting L equal to R to get the second one, I guess. Or that's part of it anyway.
Okay.
It's so weird, isn't it? You just want to say, well, they're just equal, but I guess it depends on how it's defined. Isn't that funny? Yeah. I guess it's no different than when you try and like, when they give you a problem like, yeah, like you said, like 1 over x, and you want to integrate it from like -2 to 3, and you just say, okay, oh, well, that's not going to work, is it? Well, maybe 1 over x squared. Is that the way?
Oh,
Yeah,
if you
1
want
over
like
x.
positive, yeah.
Let's say it's 1 over x squared, and I want to integrate it from -2 to 3. And so I just sort of say to myself, okay, I'm going to say the integral is -1 over x, right? And then I'm going to plug in the upper and lower bounds and take the difference. But if I'm not careful, I forget that there's an infinite like asymptote in the middle, and I got supposed to split it into two parts.
Mm-hmm.
Yeah, yeah, I've gotten caught by that before.
Yeah.
I guess most of us probably have.
Sage, that's super exciting. Have fun. Um, and so yeah, they actually give f of x equals x as an example of like a function that works for one but not the other.
Oh yeah, there it is. Yep.
It's kind of interesting that like they say that like you frequently uh just make sure the first case converges and then do the easier second case to actually evaluate it.
Yeah.
Fair enough, Sage. PD, I'm not sure what that means. Okay. Oh, okay. You know, with these rational function integrals, it's really interesting to me that there needs to be, for it to converge, the degree on the bottom has to be 2 more, not just 1 more.
Yeah, I noticed that too.
And
It's yeah, you're probably about to. Yeah, sorry, I
I
interrupted
was
you.
probably like
Go ahead.
a log thing, right? Is that
That's kind of what I'm thinking. Yeah, because if it's because like 1 over x squared, it converges, right? But 1 over x doesn't. So if the difference is 1, then that probably means you can't guarantee that it's going to converge. Where if the difference is 2, you probably can. But I mean, they actually prove it in a couple pages, don't they? I think they did prove that as a theorem.
Yeah, I was kind of thinking about it in terms of like the limit comparison test for series.
Yeah.
Because I bet that works for
Yeah,
integrals
exactly.
too. So,
Yeah. Yeah, it feels like there's lots of little warning signs in this chapter, like pay attention to this little sticking point here.
yeah, there's a couple of subtleties that I think I would have messed up in these examples.
Oh, I fully expect to still mess them up.
Yeah, yeah, same. So then we go from rational functions to rational functions times basically a trig function or exponential.
Yeah.
But the trig functions are just kind of versions of the exponential.
Yeah, this one was sneaky. I went through this one today and got most of the way through it, but I wasn't. And I even said to myself at one point, "Oh, I got to be careful of whether A is bigger than B or less than B," but I forgot to do that at the end.
Hmm. It's important for Fourier transform. Uh
Oh no, that's not this one. That's one coming up later.
oh, I remember what you're talking about. Like, yeah, there's an a minus b and then an a plus b thing.
Yeah, and they were using the SGN function to say whether it was positive or negative. Yeah, that's
Yeah.
the one. Yeah.
I was like, man, if we're using the SGN function, I feel like I don't know. Not that it's wrong, but just that it's kind of like cumbersome.
It's just difficult, If they were numbers instead of letters, you could be like, "Well, I know what this is."
Yeah. Um. Okay, and they gave this sort of other uniform convergence definition. That's kind of snuck in here.
Yeah.
Say that f of z approaches zero uniformly as r goes to infinity in CR if you can bound f of z by k sub r, and that k sub r depends only on r and not the argument of z, which the not arg z thing kind of makes sense to me, but it feels like I definitely don't quite understand a lot about this definition. It feels like a
Yeah.
version of like, uniform convergence of like a series, but instead of what, like n and x, it's r and arg z. But I wonder why one of them takes on, like, why r takes on the role of, I guess it'd be n, and arg z takes on the role of x.
Oh, I see what you're saying. Yeah, uniform, because it's like uniform convergence.
Yeah, and so I
Hmm.
think it's enforcing something kind of like continuity,
Hmm.
or like continuity is like, at least like a piece of what it's enforcing at least. Because if you did have some kind of discontinuity, then your bound would definitely depend on the angle that you're coming in from. But there's probably a little bit more to it than that. But yeah, they use this to establish, or yeah, to help with Jordan's lemma. Uh, so FC approaches zero uniformly as r goes to infinity. Then the integral for an infinite circle of e to the ikz f of z is 0, which looks a lot like a Fourier or Laplace transform. I can't remember which one.
Oh.
Oh wait, so circular arc configure 4.2.1. I want to. Is that just an upper? Yeah, that's an upper plane circular
Yeah.
arc. But
Yeah.
they say that you could also rotate that for any angle.
Yeah. Yeah, they even say you could do left circles and left semicircles and right semicircles. I remember reading that somewhere.
Yeah, I think that was earlier.
Okay.
Okay, here's the I guess alpha minus beta thing.
Yeah, this is the one that I sort of messed up. I got a long way with it.
Yeah, like you have to use a sum to product to like split it up in a nicer way, or product to sum.
Yeah. Yeah. Yeah, so depending on whether A and B are which one's bigger, you're either in an upper semicircle or a lower semicircle. Alpha and beta. Sorry, did I say A and B? I'm talking about alpha and beta.
About the same. Um,
Now, what about if alpha was equal to beta? That's the other thing I was wondering.
they address that at the end.
They did say that? Yeah, okay.
I think if alpha, uh, one of them zeroes out, but where did they say that? Yeah. If we take sine of 0 equal to 0, then alpha equals beta is incorporated in this result. Towards the bottom of the page. Hey, Anurag.
I do remember noticing that it was coming out to be odd. Because when I did 2 pi I times the residues, am I thinking about this right? I because there was a because for these ones I remember they said when you did 2 pi I times the residues, you would get a complex number and you would get the real part and the imaginary part, right? And the real part would go with the cosine fx cosine x, and the imaginary part would go with fx times sine x. And when I did it, I think I got a pure imaginary, and I was like, oh, that's good. That's what I was looking for.
Okay.
We'll probably see something like that in the problems.
Probably, yeah. Um, then we can do rational functions of sine and cosine from 0 to 2 pi. Which this substitution was kind of crazy. But it's cool how it works out. Oh, I didn't... I couldn't follow the very last thing they said where the residue calculation must find the zeros of a polynomial. That's because I'm not very good with residues.
The fact that fxy is rational function of xy implies that the residue calculation amounts to finding zeros of a polynomial. Well, I guess if it's a rational function, you can always break up the denominator into linear factors, right? To find all your find all your zeros of your denominator. And yeah, I guess that's why.
I guess so. You can... It'll just be like poles.
Yeah. Yeah, they'd be poles, wouldn't they?
Okay.
Yeah, I guess if it's a rational function, you have to have just poles, right? Of any finite order. Yeah, this was the last example I got up to in the reading. 4.2.4. And then I was scrolled ahead and was like, oh my God, how long is this section?
Yeah. I don't think there was much more after this. Um, yeah, I don't know what to say about that one.
I thought I was going to have to consider cases on B for 4.2.4. And I could see they did B equals 0. And I was thinking, okay, I knew I was going to get 2 pi over A, but I thought you had to be concerned with whether B was positive or negative.
Hmm.
Maybe they just meant us to assume that B was positive. They said A was positive, but they didn't say B was positive.
Where does B being negative affect it?
Yeah, I was okay. Well, what about Z1 and Z2? They're finding the roots of the denominator. When they use the quadratic formula or whatever, when they pull that B out, wouldn't it have to be absolute value of B? Because it was the square root of A over B squared minus 1. And if they pull a B out, wouldn't you get 1 over absolute value of B? It's probably not worth worrying about. I just noticed it.
Oh.
You know what it was? I was once bitten, twice shy because I just did the problem with the alpha and beta and hadn't paid enough attention to the signs. So for this one, I was paying lots of attention to the signs.
uh, it might be okay because of, well, yeah, there's a negative sign in front that might make it agree, but I don't know. There might be another issue with that.
You might be right. It might just not make a difference. It might honestly not make a difference if B is positive or negative.
Yeah, because it's a good thing to like watch out for, but it might just happen to work out here anyway.
Yeah.
I'm not completely clear though.
I was trying to think of what the graph would look like, right? So we're 1 over A plus B sine theta. And they made sure that the size of B was less than the size of A. And that makes sense because if the size of B was bigger than the size of A, that thing would go that you'd be dividing by 0 at
Isn't it like a spiral in regular polar?
Oh yeah, let's graph it maybe.
Why is that a parabola? That's if A equals B. We want A greater than B. Really?
It's an ellipse.
It kind of.
Okay.
I feel like I remember seeing this as a conic section. Actually, that kind of makes sense.
Yeah, it's a conic section, isn't it? What happens if you make A smaller and make B bigger? Let's just see. I just want to see.
Wait. If A is smaller.
Yeah, what would happen? Is that what you had before, right?
Ooh,
I guess if A
hyperbola.
equals.
Yeah, I think somewhere in here is like the eccentricity with the A and the B.
Yeah, yeah. Yeah, Zach was doing an integral today on his channel. He was talking about the eccentricity. And I think it
Oh, I
was
saw
sort of
that.
similar
Yeah.
to this, maybe. And he was doing one of those ones with the Weierstrass substitution. And I was like, is the Weierstrass substitution just like a real substitution that's similar to this complex substitution we're doing for these rational trig functions? I feel like there might be a relationship between them.
As far as I know, it's just a really clever real substitution. This is the one-dimensional stereographic projection of the unit circle parameterized by the angle measure onto the real line. Whoa.
I think stereographic projections isn't that the Riemann sphere? Isn't that stereographic?
That's an example of one, yeah. I think
Okay.
they're more general than that. Michael Spivak called it the world's sneakiest substitution. Um,
It is pretty sneaky.
as far as I know, it doesn't have anything to do with complex numbers. It's just an alternative way of doing it.
Hmm.
Slim is saying may not matter if you do plus and minus the root. I think in regards to the sign of b thing, you could have absolute value and take out. So I'm saying it is true that you would get the absolute value when you factor the b out, but it may not matter.
Yeah. Yeah, maybe not.
Oh dang, Perva. I'm sorry to hear that.
And then there was this crazy rectangle. I didn't really look at it.
Yeah, I was kind of puzzled by the n+1/2 thing, but I realized that with the way they constructed the integral, that's where cotangent has asymptotes at, because it's cotangent of pi times zeta. So at integer zeta, there's an asymptote.
Okay.
The height of the rectangle, or sorry, the width of the rectangle, ni just kind of seems arbitrary. Or no, that is the height. This is where it got seriously crazy, though.
Yeah, I didn't even look at this one.
Just wait. There's gonna be one that or there's gonna be like some steps in here that are just wild. They seem to have an important point for it though. Um, yeah, okay, it's the bounding stuff that I thought was really crazy. It sounds like you tried as hard as you could, Proper. Hopefully you get another shot at it. So yeah, I just kind of believed them with this part of it because this is just too many letters.
Yeah, you know, zetas and etas.
I understood the idea of this kind of just boils down to using identities, but I didn't. There's way too much to read to really dissect any of this for me.
Look what they said there. They said this formula 428 is referred to as a Mittag-Leffler expansion.
Yeah, I think that was the important thing that they wanted to show.
And then they said they discussed that in 3.6 of chapter 3, which had a star on it. Didn't it? Because I don't think I had read that part.
Yeah, I think it was starred.
An expansion based upon the poles of the function cotan of pi of z. That's sounds kind of cool.
Yeah. And then they use that to get an infinite product representation for sine of pi z, because you can integrate it to get log of sine pi z, which is all this stuff was crazy. Like I would never know to do this stuff. I was just like blindly exploring math on my own, but
No, you'd have to be. That's like Ramanujan level stuff.
yeah. And the way that they figured out these a0 and a sub n constants is it was wild. I had to think about it for a while to make sense of it.
This is an example of the so-called Weierstrass factor theorem discussed in section 3.6. Oh, it sounds like we skipped a bunch of stuff in 3.6 that would have helped.
Yeah. And so I think this isn't the important part of the section, but
Yeah.
yeah. And then they show a second way of getting the same result with an even crazier integral. And they introduced like this. It made me laugh. Like sigma prime
Yeah, what is that sigma prime? That's what I was just looking at, the little
Yeah.
apostrophe. What the hell is
It's
that?
like, is that a derivative or but they explain at the end that you skip over n equals 0.
Oh, it just means don't include 0. Oh.
And that's because we're evaluating zeta equals n. And there's a 1 over zeta. The zeta minus z we don't have to worry about because I think we're already saying z isn't an integer.
Okay, well, I have no idea what any of this is.
Yeah, me neither. Ugh. Okay, then back to things that are more sane but still weird. 4.2.7. 1 over x
Okay.
cubed plus a cubed. And to me the thing that I like part through the paragraph they said, nevertheless there is a symmetry that can be employed that x e to the 2 pi I over 3 cubed equals x cubed. The word symmetry there is really interesting to me. Like, I don't know what's symmetric about that.
Hmm.
But for whatever reason, that implies that you should use a contour that's basically like a circular sector with that 2 pi over 3 angle.
Wow, that's a cool one.
Can they just... Skitty is asking... Oh, I've seen that too, Skitty. I think
And not
they
equal
also
0.
did
Yeah.
n not equal 0 on the end.
Yeah, don't they usually write like n not equal 0 underneath the other like index notation? I think I've
Yeah.
seen that before.
I think maybe that's just... We can chalk that up to weird things this book does. That's not the only thing.
Yeah, that's Ablowitz and Focus trying to push the envelope with their new notation.
Yeah. I was just thinking about, like, the deeper I've gone into math, the worse the notation seems to get. But I can't necessarily, like, suggest a better one. Yeah. Um, okay, and so part of the difficulty with the integral that with this integral set, it goes from 0 to infinity, not minus infinity to infinity.
Right.
Um,
Well, that's good to know that there's some kind of trick for something like that.
yeah. I kind of want to get into the problem soon, so I don't want to like go into like every last step of this, but
Yeah, fair enough.
um then cosine of tx squared, sine of tx squared. They do just a wedge with angle pi over 4.
Oh.
The pizza slice, yeah. Oh yeah, and they the integral, the Gaussian, or the Gaussian integral, whatever it's called, like that integral comes up. They somehow
Oh yeah.
do some
Yep.
magic to make it look like that. And Mulik, I'm not doing question and answer right now, but if you want to talk in like an hour and a half or something, we can. I don't know that much about the gamma function though. They also do e to the px over 1 plus e to the x. And the real part of p has to be less than 1. Which I was wondering why only the real part had to be less than 1, but I guess the imaginary part just produces a rotation and wouldn't make it blow up to infinity or anything like that. Okay, but that was the last one that you did.
Yeah, there's a lot of examples, and a lot of them seemed kind of intense, you know?
Yeah. None of these were easy integrals. So I got expecting to just like look at a problem and then be like, okay, which example is related to it, and then kind of hopefully be able to copy the steps for that problem. That's what I'm hoping for.
Yeah.
All right, do you want to get some problems?
You know it.
All right. So from section 4.1, first one I said was number 2. I said, I think just A for that one. Okay. 1 over 2 pi I integral f of z, which this is equal to the residue.
C is the unit circle.
Yep. Do these problems by enclosing, or by both enclosing the singular points inside C and enclosing the singular points outside C, including the point at infinity.
Okay.
Okay, so a squared is less than 1. So we're enclosing 2 singular points,
Yeah.
plus and minus a.
Yep.
And so we probably want to find the residue at each of these.
Yeah.
Might need, oh, actually partial fractions. We'd have to do division first. Maybe we don't need partial fractions. It's just a rational function. We should have a formula here.
Yeah.
They're both simple
10.
poles, so we can do, the one you said.
Yeah, that one is pretty cool. That one is pretty cool.
And we're gonna add the residues. So we're gonna evaluate the top at A divided by the derivative of the bottom evaluated at A plus the top evaluated at minus A divided by the derivative of the bottom at minus A. 0.
Well, that's nice.
It's an even function.
Yeah.
Maybe that's why we get 0. Something like that.
Yeah, maybe if it's an even function and its poles are on the real axis, then maybe the residues have to cancel out.
Maybe, yeah.
Hmm.
We'd have to do it the other way, which is the residue at infinity.
Yeah, what does that mean? Enclosing the singular points outside. Let's see. Oh, by including the point at infinity. Oh, I see. Because we have to worry about infinity.
Yeah.
Okay.
Limit as z goes to infinity of z f of z. If f of infinity is 0. Oh, it's not 0 here, though, is it? It's 1.
Hmm.
So this formula doesn't work.
Well, we could do the 1 over t squared f of 1 over t. And then do
Yeah. How many variables can I manage? Not that many, apparently.
What's this epsilon here mean again? Oh, that means
Uh,
there's a pole at 0 or something?
Instead of doing an infinitely large circle, I'm doing an infinitely small circle for
Oh, yeah.
infinity.
Okay. Okay.
Uh, do, do, do. I thought you were complex. Hopefully this is a good thing. Oh yeah, so we're gonna want 0. So if we can just find that we're not including any poles, then hopefully we'll be okay. I multiply this down at the bottom.
Okay.
We're going to get a squared t squared minus 1 dt, and then bring that down. Oh, we got a double pull at 0. Okay, well. The difference in the powers is 2, though. So I think we can safely say that whatever pull we get from that is going to be outside the contour.
Yeah, because that's plus minus 1 over a, isn't it?
Yeah.
So even if a is less, yeah, if a is less than 1, then 1 over a will be outside the circle. Yeah.
Yeah, a is a finite number,
Outside the
so
unit circle.
yeah.
Yeah.
All right, good night, mouse. And so how do we want to...
Mouse, I owe you.
I don't know why, but apparently you do.
Yeah, what do we do now? I don't know how to do these infinity ones.
Well, now it amounts to just finding the residue for, I guess, the inside of the integral around 0.
You're saying the pole at 0, right?
Yeah.
Oh.
Maybe that's the formula
Could
involving
we...
derivatives?
Well, wait, it should be nothing, shouldn't it? Hang on, how do you do this? Yeah, you know what I want to do?
What's that?
Tell me if you like this idea. Does that work? So, because we're worried about when t is 0, right?
Mm-hmm.
So when t is 0, this function on top is fine, right? We just get negative 1. So it basically looks like negative 1 over t squared when t is very close to 0. And so, is that good? Can I just say that? And so then the residue is 0 because there's nothing over t, it's just over t squared. I mean, I'm not very convinced by that, but maybe.
I want to try applying the formula he gives and see if it agrees, I guess.
Which formula? Yeah, we should try a formula.
I want to do... I'll take a screenshot of it and, like, bring it in, I guess.
Oh, 4.1.7.
Yeah, because phi is just the new... it's probably what you wrote, actually, like the numerator of what you wrote.
Yeah, the phi is the numerator, isn't it?
Yeah, but we still have to include the a squared t squared minus 1, I think.
Okay, I'm going to erase what I wrote here because I'm not too convinced of that.
Okay.
I don't think it was wrong, but it might not be going the right way.
I think phi is 1 plus t squared over a squared t squared minus 1. And if this is a double pole at 0, we're going to take one derivative evaluated at t equals 0. And that's a thing. Hopefully. Since it is a double pole, don't you need to take the derivative of the numerator to find the residue? Yes. Oh, you're saying that to what Fenlox was saying, Slim? Probably. We do need to do a quotient rule, which is unfortunate. Low d high minus high d low so you're doing now. Okay. So
yeah, because if it's a second order,
0 minus 0 divided by not 0. Aha. So we're good. Oh,
you got 0?
Yeah, the c sub -1 is 0.
Okay. Well, we did want that because that's what we got from part A, right?
Yeah. So I feel a lot better about it now.
Cool.
Okay, next one. Yeah.
So you just had to use the quotient rule and then plug in 0. Okay, I get it.
Yeah. This one had quite a few parts, but I think I only chose 2 of them for us to actually do. 3, A, and C.
Oh, classify the singular points. I'm bad at these.
So this is specifically at infinity. So
Oh, and I'm even worse at those.
that's why I chose this one, because we should at least do it a little bit. I'm not good at that either. When Slim was in high school and didn't know the answer to a math problem, he would randomly decide between 0, 1, -1, or E. Those aren't bad guesses. She's gonna choose a random one. Um,
Positive integer. So let's just choose 1. How about? So Z or Z squared.
wait, for this one, this is not a good one to guess 1 on. That's not a type of singular point.
No, I mean for M, because M's a positive
Oh,
integer.
okay,
So
okay.
I'm just saying, oh, let's make it equal to 1 to make it easy.
I'll just like think about it.
Unless it depends on M, but I don't feel like it would depend on M.
No, I have a feeling
It
it's going to
might.
be a pole of order
Maybe
M.
it's a pole of order M or something.
Yeah.
Oh.
Um, and so if 1 over t to the m, that's just a pole of order m at 0. That means z has a pole of order m at infinity, I think. I think it's all the work we need to do for part A.
Wait a second now. I'm not following this.
Um,
If we replace Z with 1 over T, what does that mean? That's like I feel like that's inversion somehow.
yeah.
Changing 0 to infinity and infinity to 0, and all the numbers in between are getting flipped somehow. So 1 goes back to 1, and everything else gets kind of inverted. Okay.
And so for thinking about that, we care about when t goes to 0.
Yeah. So you're saying that's a pole of order M at 0.
Mm-hmm.
So that means we have a pole of order M at infinity for the first thing?
I think so.
Okay.
It's my logic, at least.
So let's just say it was Z squared. So we're trying to say Z squared has a pole of order 2 at the point at infinity.
Yep.
Yeah, I desperately want to imagine in my head what that looks like, but I probably shouldn't even bother trying.
Me neither. I'm also confused on the concept of whether it's isolated or not, because I think of infinity as a circle in the complex plane.
Mm.
But like it can still be an isolated. I think this is an isolated point, but I'm still confused with like how it's a circle and it's isolated. Maybe it's not isolated, but I feel like it is.
Well, once we're finished with this, maybe we should check the answer.
Oh yeah, this one is odd. Yeah. Part C. One of the infinity is the north pole of the Riemann sphere. You could. And inversion flips the Riemann sphere upside down. I don't know how to think of that. Well, I guess that answers the isolated part. Yeah. I guess it's fair. Just there's nothing around the North Pole that's also isolated. Yeah. Fair, fair. Um,
Z squared plus A squared to the 1/2 power.
and a squared is greater than 0. Why don't they just say a real? Or to use inversion and conjugation. Oh, yeah. So, can we say there are no singular
I
points?
was reading about that stuff in VCA. Yes, I was. Chapter 3 recently.
Okay.
Very cool.
So are there
So should
singular
we just do the
points
same
that are
trick?
finite? I feel like there wouldn't be. The same trick? Maybe. I don't know how it's going to look here, though.
What about the square root function? That's fine everywhere, isn't it? You can take the square root of any complex number. And you get 2 answers, don't you?
Yeah, I'm wondering about, like, maybe branch cuts.
Oh.
But I don't understand much. The book said at one point there's some relation between branch cuts and singular points, but I don't know.
That's right, because there's a branch point for this function at 0. Is that right? No, wait a second. Z equals plus minus IA, is that right? If I let Z equal plus or minus I times A, then I got the square root of 0.
Mm-hmm.
So does that mean we have 2 branch points? I think we
I
do.
think so. That's a section that we skipped over that I'm going to go back to on my own time at some point.
You know what? I did read it a little bit. And if you have 2 branch points like that, you don't need 2 branch cut. You can make 1 branch cut that joins the 2 branch points.
Oh.
Yeah, so we might have something where Z is plus or minus I times A. So we were saying A was real, right?
Mm-hmm.
So maybe we've got something that looks like this. Maybe here's IA and minus IA. Those are our branch points. And maybe this can be the branch cut, maybe. Oh, my handwriting's not good. You can read it.
Yeah. There's a little like branch out, but it's close enough.
It does look like branch out. Branch out.
Like I gotta branch out to complex analysis.
I think you're being kind. It looks much worse than branch out. Oh, now it's got a low C. All right.
Yeah.
Anyway, how would that help us? Because I'll tell you why. Because they said if you had 1 branch point and you wanted to do a branch cut. No, I'm going to be talking a little bit out of my area here, but I think they said you got to do a branch cut from the branch point out to infinity, right? That's how they were doing that. But here, where you had 2 branch points and you could do a branch cut to join them, you didn't have to have a branch point at infinity.
Yeah.
For some reason.
Which,
so
yeah, that's kind of weird. I don't know if this matters for the singularities, but
yeah, it might not.
I don't think I'm worried about it because the book did say there's some relationship between branch cuts and singularities, but I don't really. I don't know. If there's one here, I don't see it.
So you know what I think this means in this picture? As long as I did any kind of loop like this, if I was out here and I didn't cross that branch cut, then that contour, if I integrate around that contour for this function, I should get 0.
Yeah.
But if I cross over that branch cut, is that right? What if I did something like this though? What if I had a contour like this that cuts the branch cut twice? Look at that.
Ooh.
No, I haven't gone around either one of those. I haven't gone around either one of those singular those branch points.
Dude, yeah, that's a funny question.
Because I could have made my branch. I could have defined my branch cut to be over here, couldn't I? Like there.
Oh, yeah,
And then,
for that contour, you'd define a different one.
and then the second one would have missed it.
Yeah, because like if like I think like maybe like log is the easier one to think about for this. If you had a like normally the branch cut for log we've been saying is like that, but if you had a contour that was like that, oop, that was like that, you'd want to draw that branch cut or something instead. So maybe that's the idea.
Yeah.
Could you do like the inverse branch cut with the square root thing? Could you do like each one out to infinity?
Yeah, I think it said you can. You can do it that way.
Okay.
Or you can just join them somehow. Anyway, but let's look at the algebra you were doing. So what does that tell us?
So pull of order 1 at
factor that
0 or at infinity. Yeah, I got a common denominator and then square at the top and bottom. I didn't realize it'd be that
So
queer.
what did you see? It's a pole of order 1?
Yeah, just from looking at the final step there, like if the function of t has a pull at 0, then the thing with z has a pull at infinity. So we can check our answers.
Yeah, let's check them.
All right, 4.1, 3a and c.
Slim says, what happens if the circle encloses the branch cut?
I think you get like enclosing the entire branch cut.
Oh yeah, if oh yeah, I see what he's saying. Yeah, if I go around like the whole thing like this, then I think that would be zero.
Probably, yeah.
Yeah, I think so. Yeah, I think you're just not supposed to cross the branch cut. I think you're not supposed to cross the branch cut. As long as you don't cross it, you can guarantee that your contour integral is 0, I think.
I think so, yeah.
But I want to know what happens if I cross it twice like this. I feel like I should still get 0. Maybe you can count the number of times you cross it. Oh, you got it right? Pole of order m and pole of order 1? Oh, okay.
Yeah.
All right, nice.
Okay. Number 6 is the last one I had from this section. This one I think was more of a challenge one, or it looked a little bit more like challenging though.
We're integrating over a square again.
Yeah. Square centered at the origin.
One over z squared cosh z. Cosh. Oh yeah, cosh can be 0, can't it? Cosh of a
No.
complex number.
Oh, cosh of a complex number, maybe.
I think it can. Yeah, because Koch is 0 when e to the IZ is minus e to the minus IZ.
I bet it's gonna be like purely imaginary numbers because that's gonna make it look like cosine. Like it'll be like I pi over 2, 3 pi over 2, maybe.
Hmm.
Both are residues and by direct evaluation. Actually, we actually do need to answer this question. Or like we do need to figure that piece out to answer this, I guess.
Yeah, I feel like we've got to work out where those zeros are. Okay, so
Cosh IZ is cosine Z. Or do we want the other one? Cosh Z is I cosine, or cosine IZ. Ugh.
Don, I'm going to be back in 1 minute. I'll just
Okay,
mute for a second.
no worries. Yeah, and so I think from this, cosh of Z is 0 when cosine of IZ is 0, and cosine of IZ is 0 when pi over 2 plus k pi. I think we need I pi over 2 plus k pi. Actually, yeah, the other relationship is maybe more clear.
Okay, I'm back.
Okay. So I think the zeros of cosh are at I times pi over 2 plus k pi.
Nice. Okay, looks good. Oh, so they're on the imaginary axis.
Yeah.
And then we've got a pole of order 2 at the origin.
Oh, okay. I was about to say it might be order 3 because of the
Oh,
the cosh, but no, cosh 0 is not 0. So it's only order 2. Yeah, yeah.
so now this is, let's see. So are we going to have to use that residue formula?
We can definitely use it for the z squared piece. The cosh piece, I'm not sure about.
Yeah, the cosh is tricky, isn't it? The z squared we can think of it as 1 over cosh over z squared. And then the residue will be 1 over cosh over 2z. And then plug in, oh wait, that's trouble. That's trouble.
Well, we need to do a derivative because it's a double pole. I
Yeah.
just don't know what this derivative is. Remember, cosh is hyperbolic secant. Oh, which is minus secant tangent. And so phi prime of...
Tan H.
Yeah, thank you. Hyperbolic secant of 0 is 1 over cosine of 0, or cosh. But that's just 1. Hyperbolic tangent, hell if I know that one. I think it's 0.
I would think so.
It should be odd, right? Oh, wait, hyperbolic tangent looks like arctan? Whoa. I don't know that. I need to see it to believe it. It does look like arctan. Okay. So...
Paul's online notes.
yeah. Comes to the rescue. So we get another 0 residue around 0 this time. Now, how about the residues?
How did you get that?
I use the same formula we used before. 4.1.7, or the one I took a screenshot of. When we did it at infinity. Yeah.
Oh,
this
so
one.
you're saying M equals 2.
Yeah.
Oh. Okay. Okay, then what do we do with this cosh?
That is the question.
Okay. Can we write cosh? No, it's not going to help. Oh, wait. Can we write cosh as a series, which is
The even. Z to the 2n
yeah,
over 2n
one
factorial.
plus, yes. And they're all positive, aren't they?
Oh, yeah. Are there... yeah, it's just a combination of e's, so there should only be positive terms, right?
Yeah.
So that means c sub negative 1 is 0? That doesn't make
I don't
sense.
know. How'd you work that out?
Well, because if we're saying the series for cosh only has positive terms, the residue is the negative 1 term. Unless that expansion is only for real numbers, and for complex numbers it's something else. Cosh in the denominator. Ah. That's a good point, Slim. How does that change then when Kosh is in the... well, obviously it flips, but... do they just give us that series, or probably...
Does this help? Oh, and then we multiply by z squared, but then we don't really want to multiply by z squared, do we?
Um...
Maybe we can use L'Hopital's rule. Because I think they said the residue is like the limit as you let z approach the singular point of the function times z minus the singular point. So we're gonna get 0 over 0, but then maybe we can hit it with L'Hopital's rule, and maybe that'll help.
Wait, what limit are you taking?
I am thinking. Okay, you know what? Yeah, where's the book? I'm gonna look in the book. You're looking in the book. I could be wrong about this. I thought we could get a residue as a limit. Oh yeah. Yeah, okay. 4.1.8, which is page 210.
4.1.8.
Yeah.
Okay.
And if it's a simple pole, and I think these are all simple poles, then the residue is the limit as z approaches that z0, whatever the point is, of the function z times z minus z0. So it's kind of like you're right. It's kind of like you're multiplying by z minus z0, so you can cancel out the zeros from the top and bottom of your expression.
Why are these simple though?
Okay. Why are they simple poles? Well, okay, you got me there. I was just assuming they were all I was just assuming they were all simple poles. Are they simple poles or aren't they?
um So my mind was
Yeah.
going to we have to do that weird like geometric series trick that they were doing that we were talking about last week. I guess we are getting the Laurent expansion around a singular point. So z minus I pi over 2 plus k pi. Ugh. Um, and so we only care about well, we need, like, if we can just get the first few terms of what the series looks like, that will be enough to
Oh.
figure out the c sub -1, was my thought. It's like, we would flip all these terms to be negative and have it to be 1 minus all of that stuff. Ooh. Yeah, this is weird. Plus dot dot dot. And this series goes from n equals 0 to infinity to the n. I don't think this is a good thing.
I got confused.
Oh wait, actually, I mean, the minus would be on the inside. But
You
like,
said we're using like a geometric trick, right?
yeah, I'm thinking of this as like 1 over 1
1 minus
minus
a
negative,
negative.
negative,
Yeah.
like that.
Okay,
Then
okay,
this
okay.
entire thing is r, which is the bit that makes it weird.
Okay.
I discover hate in an unexpected place, color cone. Ugh. I don't think this is what we wanted. I don't know. I think this still isn't getting a c sub negative 1 term.
Hmm.
Because these are all like positive powers of z. There's no negatives.
Let's try what I said for a second.
Okay, you do it, because I wasn't following.
Okay. I'm going to say this. I'm going to say f of z is 1 over c squared cosh z. I want to find a residue of f of z at z equals I times pi over 2 plus k pi. And I want to say that's equal to the limit as z approaches. Can I just call this alpha? This is called alpha now.
Yeah.
I'm going to call this alpha. Z approaches alpha of f of z times z minus alpha, which is, okay, let's write that. Because we already know this should be 0 over 0, right? I mean, that's what it's going to be. Oops, I forgot the f of... No, that's right. Am I getting confused? Cosh z. Now, assuming alpha is a root of cosh, right? Then this is 0 over 0, isn't it? Now, then can I say by L'Hopital's rule, it should be 1 over... Oh, but I need the product rule down here. Is this... Because this is not going to help, is it? Because I'm still going to get a cosh. It doesn't work. Unless, can I put the z squared? Nope. Can I put the one, can I move the z squared upstairs and make it 1 over z squared times, maybe I could try that. Let's try this. I feel like this is not going to work. Oh, what's all this awful business? Has it worked? Let's see. You get 1 over z squared over, maybe this works. Does this work? Maybe this worked.
I think since should be 1 or negative 1.
Because the top now is just going to give me 1 over z squared, isn't it?
I think we have that formula, color cone. I just don't know what the... We haven't really shown what the order pull is for Kosh, though. This, if we're getting right here with what Thanos is doing, I think we're getting lucky that it's a simple pull, but we haven't shown that.
Well, lucky is my middle name.
1 over alpha squared over sinh of alpha.
Yeah, so what did you say the sinh of alpha was going to be?
I think it's 1 or -1 because we engineered it so that cosh is 0. It depends on our choice of k.
Does it? Okay. So it's like flipping back and forth between 1 and
Which I guess
-1.
we could sinh of I pi over 2 plus k pi
Yeah, we should probably work it out.
is equal to sine of just pi over 2 plus k pi.
Oh. Which
So
is cosine k pi.
oh yeah, it will be cosine k pi.
And k is an integer?
Yeah.
So it is plus -1. Okay, so -1 to the k. Okay.
Yes.
So and then we got to take the whole alpha and square it. So that gives us a -1. Doesn't this feel like a Fourier series or something? This is weird.
I don't know. Wait, isn't the sinh -1 to the k?
Yeah, I was going to move that upstairs. I think we get this. Oops.
Oh yeah, because the alpha. I see. Yeah, they're trading places.
Because when I squared the alpha, I got another -1 coming out.
Yeah, because of the I. Okay.
So then we have to do what? Take a
So
sum
that's
of all these residues from.
are they summing to
R.
0? So if this is a simple pole, we get alternating signs. I feel like we're enclosing pairs.
Yeah, we're definitely enclosing pairs.
And that those pairs have opposite signs.
Do they?
They're saying in either case, limit as r goes to infinity of I sub r is 0. So in the long run, it should be 0. It might be 0 in
Oh,
the
they're
short run
telling us
also.
it's supposed to be 0. Oh. Where the limit is taken over the integers.
Maybe they're saying this r plus 1 pi thing because we're probably
Yeah.
enclosing r many poles? Or 2r, maybe.
Oh, that's right, because you said the poles are odd or plus pi over 2. Oh, so the poles will be like plus minus pi over 2 and 3 pi over 2 and 5 pi over 2. Okay. So r plus 1 pi. Yeah, maybe you're right. Maybe there's r many poles. Yeah. On each side, right?
Yeah, 2r in total.
2r total. Plus the 1 at 0, but we said that gave us nothing. But if I let k equal 1, wait. Oh. Yeah, I don't get it. How is this going to add up to 0? Maybe I got a mistake here, Don. I felt like that L'Hopital got me through it, but I might have made a mistake.
I don't know.
So what are we trying to do then? We're trying to add up all the k's from, we want k to be from minus r to r, right?
Yeah, there's probably a relationship between K and
Yeah.
R that we can find.
Yeah, I feel like the k we want, we want to add up all the k's from minus r to r. Wait a second.
It's like if R equals 0, we're
Maybe it's
enclosing
minus r
2.
to, yeah, it might be minus r to r plus 1, or it might be minus r minus 1 to r. Because when k equals 0, we're already at the plus pi over 2 pole.
Mm-hmm. And minus pi over 2. Um, hmm.
I don't see how this could, I mean, it might add up to 0, but I don't see.
Well, it's because the residues are always canceling. So, like, even the residues from the first two poles at pi over 2 minus pi over 2, those just cancel.
Oh, sorry. Is that true? I didn't think they were, but maybe you're right. So you're saying if k is 0, I got minus 1 over 1/2 squared. And if k is negative 1, I got 1 over 1/2 squared. That's what you're saying, right?
Uh,
Okay, let me, you know what?
yeah.
Let's, okay, and if k equals 1, I got 1 over 3/2 squared. And if k is minus 2, I got minus 1 over 3/2 squared. All right. You know what? You convinced me. You convinced me. They're symmetric. Damn
Okay.
it. Why didn't
So, Kalikon, the problem is, well, the first problem is we never proved that these poles are simple for the Kosh part. The second part, the second problem is that we are supposed to get 0 as R goes out to infinity. Here's the original problem. Uh, and we're just kind of getting 0 immediately, not even in the long run. And so we're not sure if that's right or wrong. Shug, I'm always acting up. Hope you're doing well. Um,
Yeah, we didn't do the line integral.
take the derivative of Kosh, you don't get 0 anymore, so the poles are simple. Huh. Compute the derivative of Kosh at your pole. Really? Okay. The residue, we got 0 at z equals 0. I appreciate you, Shug. You're always welcome here. I know most people don't want to, like, just watch a math stream, though, so... if you like being here, though, you're more than welcome. That's sus? That we got 0? Okay, so... I used the formula that you posted and I took one derivative of 1 over cosh and evaluated it at 0. And the thing is that hyperbolic tangent of 0 is 0. So everything is kind of zeroed out. The premise of the question wouldn't be right though if it was non-zero, unless it, because as r goes out to infinity, we do need to get 0 in total. So if we don't get 0 around z equals 0, then it needs to get canceled out somewhere else. Okay.
What did they mean when they said in the direct evaluation use estimates of the integrand? Was that for the line integrals?
Yeah, I imagine it's a very difficult line integral to actually compute.
Oh.
So you probably bound it above by something and show that it goes to 0.
Oh, good lord.
But I think let's not do that part of the question and move on. Let's try to fit something in from 4.2 because we're near the 2-hour mark already.
Okay, yeah, sure.
Okay.
Are you happy with what we did? I mean, I think we were okay.
Not entirely, but I think we're.
Yeah.
I think that's to the right answer. I would maybe do the steps a little bit differently now. And the direct evaluation is an exercise for the reader now.
Yeah.
Okay, so this from 4.2. The answer is 7. Thank you, Shug.
Yeah, so okay, I like kind of like what, who said it? Academy? Slim? Or did Collar Cone say it? But somebody said if you have a pole that's not simple, then if you take the derivative there, it's still a pole, right? You don't get rid of it. Sorry. Am I right about that or am I going backwards? Forget it. Forget it. Let's keep going.
Okay. Yeah, I'm not completely following that thought that they were posted.
I was kind of thinking of the infinite series representation of Koch, kind of like an infinite number of poles, z minus z0 and z minus z1 and z minus z2, and when you just like expand it all out, it turns into that infinite series. But you're right that there's no reason that they would have to be simple, right? I mean, I could still get a series with poles that weren't simple.
Yeah, I think you care about like whatever, if you want to read the strength of the pull from the series, you have to do whatever your highest negative power is or something like that.
Yeah. Yeah. All right, now we got an integral.
Yes. And so part A, we got sine involved.
Yep.
And so whenever sine or cosine were involved, they were making it in e to the ix. They're saying plus or minus. How do we know which one is plus or minus?
I think they said you could
for the
go
contour.
either way.
Yeah. Yeah, rational functions are a lot easier to work with, it seems. So if we do the upper half circle,
Yeah. Wait a second. X squared plus a squared.
yeah, so we're gonna have a pole at
Oh,
IA.
IA and minus. Yeah, good, good. Okay. I like it.
And so we have sine, and so we want the imaginary part of the residue.
Yeah. So I think we can call, this is the way I've been doing it, call this f of z. Now here's what I want to do again. I want to claim that there's a simple pole at z equals IA.
I agree now. It's much more
That
clear.
seems fair, right? Yeah.
Yes.
I mean, we got this e to the iz up here, but that doesn't bother us, right?
That's not going to contribute a pole now. Not
No,
unless
and
we're
I
at
can
infinity.
Oh, at infinity, yeah.
But we don't have to care about that.
And I can think of it like if this e to the iz wasn't here, we'd just have a nice rational function.
Mm-hmm.
But with the e to the iz here, I got something else going on. But I can think of it just as like a very big polynomial kind of. I just want to treat this like it's a rational function still. Kind of what I'm doing. That's kind of what I'm doing because I want to do the trick again where I can leave this as it is and take the derivative of this and then just plug in IA to get the residue.
I think they were doing something like that. It definitely looks like they took a derivative in example 4.2.2. Why does it look like... I forget the justification.
Yeah, they did, didn't they? And it's not the e to the e on top makes me think it's not a rational function. Yeah, what did they say?
You know, I did write down the integral not in the same way that they've written it in their example problem. They stayed with x's.
Actually, in the book it says it doesn't have to be rational. It just says suppose our function is given by a ratio of two functions which both are analytic in the neighborhood of z equals z0.
Oh, is that for the
right?
n over d thing?
That's for the n over d thing. Yeah, it says as long as n and d are both analytic in that neighborhood.
Okay, that's certainly true here.
And it says if that's the case, you can use, and if it's a simple pole, you can use that trick of n over d prime, n over the derivative of d. So I think we can just get away with that dirty trick.
That's the definition of being meromorphic. Collar Cone says.
Nice.
So wait, when you do this, are we ignoring the bad part of the denominator? Yeah, we are. Or
no.
No.
Well, what do you mean? No, you don't have to. You just take
the derivative.
Just change it into 2z and then plug in this in everywhere, and it just works. It's like magic. I got to think about this stuff some more.
Okay.
Because we could do it the other way. You know, we could break it up into the denominator up into factors, and we could cancel out the one that's the z minus IA, and then you plug it in, and it just still works. It just still works. It basically gives you the same answer.
I just want to look again at the n over d thing. Was it d tilde or just
1.
d?
It was section 1.
Oh, it was just d. Okay. Okay. So yeah, the z's cancel.
Beautiful.
e to the minus a over 2. That's the residue.
And that's the only pole we had, right?
Yeah, that we enclosed. And we said we have sine.
Yeah.
That would go with the imaginary part.
Oh, and there is no imaginary part. Wait, 2 pi I times this residue we need now.
Oh, true.
Yeah.
Change, thank you so much for the raid. I hope your stream was good. Welcome in. Hope you've been well. We're learning about complex analysis here. What were we playing? Control? I don't think I've heard of that. How was that game? Okay, so then the result of the integral, of the actual integral that we were interested in, x sine x over x squared plus a squared dx, is the imaginary part.
I think so.
Is this an odd number?
No.
Ah.
Yeah.
Can Wolfram figure this out?
Yeah, maybe.
Probably not symbolically, but let's see if it can. We can always do like a certain value of a, I guess. If not. Playing controls, what you're doing is not far off in terms of the universe there. Oh, is it like super complicated? Oop. Sine x squared plus a squared. Awesome game? Okay. Pi e to the minus a. Wow, it can actually do it.
Beautiful.
Okay. That's a success.
Man, I'll
What
tell you,
mark, so.
if you have the power of residues, it's kind of like being a god.
Yeah,
All of a
that's
sudden you can do.
it's so much easier than trying to mess with that integral doing anything else. Ugh. We do need a squared to be greater than 0. Why is that?
Because otherwise we might be on the real axis. The singularities could be on the real axis.
Oh, okay.
Is that true? I think so.
Yeah.
Yeah, like if a squared was negative 16, you'd have the things at plus minus 4. And then we'd be integrating right through a landmine.
Okay. Yeah, I like that. Right through a landmine. Wait, the residue at z equals ia is wrong, but we still got the right answer? What's wrong with it?
Oh. Oh no, we got it wrong. I thought we were doing great.
It's like SCP in terms of unnatural things. Ooh, cool.
Oh, did we pick the wrong sign? Evaluate Z. Yeah, but collar cone, check it out. I think it comes out the same, doesn't it? Try it. Does it? Wait, does it come out the same? How could it?
Well, with what color cone wrote, there's no derivative. This is just throwing out the bad piece of the denominator.
Yeah. Yeah, but look, the denominator there is 2z now, right? If you plug in IA there for z, your denominator is the same as our 2z denominator. It's no different. And so the z's cancel, and I think we get the same thing. Isn't that bizarre? It's like 2 ways to do it. But
well, I mean, the book gave us like for symbol polls, like I feel like the book threw a bunch of ways to do it. Lucky because of the root choice of a polynomial. So it's the book said that for a simple pole, you can take the derivative of just the denominator and then plug in the point of interest. So that's what we did. I think maybe your color code is using the general formula.
What do you mean by the root choice? Yeah, why did we choose? Well, we chose the positive root because we were integrating over the upper semicircle, right?
I think they come out to be equivalent. Because we can get what color code was saying from the formula we were using before, from 4.1.7. And we're just using a different formula. So I think we're both right.
Yeah, you're right. There's lots of ways to do it, huh? There's lots of little ways to do it, little shortcuts or something.
Yeah.
Oh, 4.1.8 and 4.1.10 both said only for a simple pole, right?
Mm-hmm.
Okay, but the 417 is for any kind of pole.
Yeah.
Okay. Well,
Okay.
I feel the power of math.
Oh, wait. Skitty is saying this integral is a good exercise in Feynman's trick. So it's integral in part D to avoid complex analysis. You're in high school, so you know Feynman's trick, but not complex analysis? Oh my god. I don't think I've seen... Actually, no, I have seen Feynman's with sine of x. That's crazy. Yeah, it's probably...
What's Feynman's trick?
That's like integration by differentiation. Like, it's like you insert a new variable and like you take the partial derivative with respect to that. You've definitely seen it somewhere. It's like a famous, like, it's not usually taught in school, but it's like on the internet, people talk about it a lot.
Okay.
It's like if you do a double integral in the wrong order, it's basically how you would reverse that. It's another way of like thinking about it. I can use it for a sine of x over x, huh? Yeah, no, I would just look it up. It's a pretty crazy trick.
Differentiating under the integral sign. Oh, we were talking about that not that long ago, weren't we?
Yeah.
But that was when it was a function of two variables and it was like a partial derivative of one variable.
But all right. I think we'll call there. Oh, next
Sounds
time.
good. Sounds good.
So I kind of so the last unstarred part of chapter 4 is 4.3 and 4.4. It's about the same page count as this time, unfortunately.
Okay.
It's like 30 pages. But I kind of want to plow through this and
Get it done.
Yeah. Because I kind of want to have my schedule like freed up. So I'm hoping that the next one will be the last reading group for this. So
okay.
Yeah.
Yeah, well, I'm glad we got through this residue stuff. This was great.
Yeah, this is like one of the coolest things to learn so far. But all right.
All right.
Thanks for being here.
Don.
Yep.
Yeah.
Talk to you later.
See ya.
Okay. Mayor, yeah, I can't promise I'm gonna do it if it's just for fun, but I'll take a look at it and say yes or no, I guess. If it's a big pain to like type up or something, I guess I wouldn't, because there's a good chance I'm just gonna want to do my complex analysis, but I don't want to just like outright say no. Just in general, I'm not a huge fan of just like people giving me challenge problems because I prefer to do homework help. But if there's a fun enough question, we can look at it. Oh wow, I pressed shuffle and it went to the song. One second. When the song comes up, we turn it up. The song. It's yeah, change. Thank you again for the raids. Sorry, it's hard to talk when we're doing the raiding groups because I don't want to cut off the conversation. But I'm glad that you've been back at streaming. Okay, YouTube's updated. Oh yeah, unpin. Yeah, introducing the new variable. Argument principles given. It's a quick proof of the fundamental theorem of algebra. Oh, really? What we're about to learn about? Cool. Solve an OD. I haven't seen that with Feynman's trick. Oh, Feynman didn't even invent it? Huh. Let me turn the music back down. Okay. This is what Mayor sent. To include most older texts and stop teaching in more modern ones? Oh, I didn't know that. All right, So wait, Skitty, if you're in high school, are you interested in competition math, or like how the hell do you know about Feynman's trick and Laplace transform in Dirichlet's integral? um I assume we would do this question. I assume we take the derivative of this inequality. They only give us the f is continuous, not differentiable, so this might be dangerous. But I don't know how else to really proceed. And then... this is a critical point somewhere, I'm sure. Or are they just at 0? E to the minus x squared is the bell curve. Yeah, it seems like a maximum. It's a really weird question, shows up a lot for some reason at your university. And let's see what we can prove, but... Oh, okay. So... both color code and Slim are posing the same counterexample. Oh yeah, that's a pretty good counterexample right there. Okay. Yeah, it should be a maximum. No worries. So yeah, I think I need to be more careful than I'm being, because they only said continuous and not differentiable, but if I just plow through that, are we... 1 is less than f prime 0 is less than 0. You probably need a limit argument here, because I don't like the thing that I've written it. You don't need derivative? Why not? Doing Olympiad math, I don't really have time to go into higher math unless I need it. For instance, Lagrange multipliers to solve inequalities. Integral tricks, I know just basic ones. You call these integration beads. I don't really know a lot of theory behind the higher level stuff. Oh, fair. Okay. Derivative doesn't work with inequality, really? Okay. Yeah, what's the hint? You know what, Skitty? Is he still going? He probably is. If you don't know Zach or e to the 2i pi, I don't think he's doing Olympiad ones, but literally right this instant, he's doing a 100 integral challenge. And he's pretty deep into it. Let me see what problem he's on, actually. Squeeze theorem? Okay. Yeah, he's on integral 75 right now. 8.5 hours. Oh my gosh. The madman. So as far as I know, he isn't doing an integration B ones, but he is doing like a 100 integral challenge. Although he's not being as interactive with chat because he's trying to focus on that. But just think that you or anyone might be interested. Sin of x less than 2, that's definitely not true for the derivative. Oh, okay. Oh, okay, so you do know Zach. Okay, good. Zach in general is awesome. Squeeze theorem. You missed the 69th one? I was distracting you with complex analysis. Fizzbuzz, is Squee known for any other theorems? I'm sure that there's many. I hope you're doing well, Fizzbuzz. I hope your vacation or whatever it was that you were on was fun. What am I gonna squeeze? Super fun? Awesome. Squeeze Jeeves. Please don't squeeze the Charmin. I see that's a brand of toilet paper. Dude, the squeeze theorem has a bunch of fun names in other languages, like the drunkard's theorem in French, I think. I keep wanting to like divide through by x and take limit as x goes to 0, but that's probably not it. Your language is called the sandwich theorem. Oh, nice. Hey, Jesu. Because it's like, it's not a given that the maximum occurs at 0. You could have a function, theoretically, that does, like, it starts here and then goes whoop, and then comes down. Um... Oh, maybe is it an extreme value thing? Should I be thinking about extreme value theorem? What does extreme value theorem say exactly? So let us say like there is a critical point, right? Then do something with that critical point. No, it's the extreme value theorem because it's skateboards. That's what makes it extreme. Does Paul not do the extreme value theorem? I was just not coming up on Google. Sandwich is actually a name. After the 4th Earl of Sandwich. That feels familiar for some reason. F is... Oh, it's only for closed and bounded intervals. I don't know what to squeeze. I've been given that hint to use a squeeze theorem. I don't know what to squeeze. I already got yelled at for trying to take a derivative. But squeeze theorem was apparently the answer. Oh, that's so stupid. I'm stupid. Oh my, okay. I see it. Thank you, Mayor. Not. I was thinking the limit as x goes to 0. I was really stuck on that. Okay. 0 is less than limit as x goes to infinity, f of x less than 0. And then at be continuous function. Hey Shanner. And so as long as we can find one and since f of x is always positive, it has to have a maximum. Well, yeah. That's literally, I think, all that you need. Ah. It's got to have a maximum somewhere. There we go. They made us prove it from first theorems and from the theorems you showed earlier by Weierstrass. Oh my god. I know what I don't know, which is everything. Okay. I would get annoyed if I had to prove this any more rigorously than I've written here, to be honest. So I'm sorry you had to do it that in depth, Mayor. The fighter crime. Hello? Okay. Barring any further questions, we're gonna do complex analysis studying. And so I still want to see the frickin' what's the deal with hyperbolic secant? How about graph theory? That's omega at you. Take that graph theory and shove it where the sun don't shine. Oh yeah, his buzz. We were just doing residues. We finally got that far. The thing that I want clarification on is you're still over 15 minutes. We're working on a particular question. Number 6 here. And we just said in a very hand-wavy way that all the poles or all the singularities from the Cauchy part of this function are order 1. And I want to actually show that. And so there's something about taking derivatives and getting 0 or non-zero, but I don't understand what that means. So I'm trying to figure that out. Oh, there's no graph theory at the university you're going to? Aw. What? How do they not have a course on graph theory? That's kind of crazy. I wouldn't want to take it myself, but like, I feel like that should be offered by pretty much any math program, right? Four courses on topology? I don't want to take one course on topology. Well, I actually might want to take one course on topology, but not anytime soon. They're going there to study topology. I think you're going to go there and study everything that exists and understand it very easily, Jasu. Because you can do everything. That's my theorem. You can do biology, physics, chemistry, math. You got it all. All right, so like I was trying to kind of follow the example like this. They do, FizzBuzz. So we figured that out. I'm kind of amazed at you if you figured that out without writing anything down. And so where's the work that we did? We just kind of we skipped straight to saying that the poles are simple without ever showing why. And that's the part that I wanted to like clarify. Looking forward to Introduction to University Math for first-year university students. Yeah, I'm sure you're going to be real challenged in that class. Are they not like starting you out with like? So, okay, at least when you apply to a school in America, you submit all your previous transcripts, and they tell you what classes that you automatically like pass out of just based off like the grade that you got in the class and what it was on. Is that not a thing for you? Like you have to do it from scratch? I don't think I think our handwriting is equally bad, Fembox. If f has a 0 at order n at z sub 0, then whenever it has a pole order n at z equals 0. Came back with pizza from the USA school system. Rez, hey, I hope you're doing well. That is all. That's all you need. Um, yeah, so change. Jasu is a smarty pants who is about to complete a PhD in biophysics in the UK and is gonna go back home to Finland and go right back into the university system and go for a bachelor's in math. I hope I got every piece of that right. And so Jess apparently has to like doesn't get any credit for the things that she's done previously and it's gonna be like taking the exact same classes as like an 18-year-old fresh out of high school. Possibly try to the issue would be the courses are so differently named and contain different things, finding coincidences might be difficult. Oh, okay. Yeah, it is fun to think about the differences or to talk about the differences between how different countries do things. Um Oh, by the way, guys, on Thursday, you may have heard us talking about it. Slim and I, Slim is going to try to sell me on actually enjoying number theory. So that'll be on Thursday, and it's going to start a little bit later than my streams normally start, like 2 hours late. I should put an announcement in my Discord too. If F has a zero order, N at Z sub zero. Okay, but how do I know the order of the zero? Compute the derivative. Well, the derivative will sometimes be zero and sometimes not be zero, depending whether it's sine or cosine, right? It's gonna cycle around. It's a phrase main of the year of math on Twitch several times, of course. Going to TwitchCon this fall, my only business card, I'm going to hand them out. That gives you the order of a zero. F has a degree of at least 1. Huh. Okay, so if we're saying if f of z just equals cosine z, like just make life even easier. We're interested in the order of, say, pi over 2 as an example. F of pi over 2, that's already 0. Oh, or sine. F has degree of at least 1, at least 2 if f... So f prime is not 0. And that's enough to conclude that the order is 1? Okay, I've never heard of that before. I can maybe see an argument for it from power series. Um... I do not have business cards. I was for there was a couple of day period where I was thinking that we need to go to TwitchCon and get a math panel going, but I decided against that. Yeah, it's in San Diego, which is like I think like a 9-hour drive for me or something. The thing is a story of something else funny here. The story of a Syrian dentist with years of experience within a hospital. Apparently, nothing that counted here in Germany had to redo med school because nothing was recognized here. Oh no. I could see that being like, yeah. I could kind of see being an administrator at the school and being like, you know, we can't read whatever language they speak in Syria. But like, that kind of sucks. Ask about a differential / functional equation. You sure can ask. I probably can't solve it, but you can ask it. Fell in love with number theory function during a reading group after you finish Relativity 1 on Saturdays 2 hours before your stream. Okay. I mean, maybe. I am... It depends how much... A, I'd have to fall in love with it. B, it depends on how much work it's going to be. I'm kind of intentionally trying to end the reading groups that I'm doing so I can be free before going to grad school and have more time to just study do some one-off studying of like of random shit. Like I want to go back and do some of the SARD stuff from the book, the complex book. I want to learn relearn a few things in ODEs and learn a few things in PDEs. Those orders are the coefficient of your Taylor series centered at z sub 0. I still don't like that it doesn't alternate, or like I still don't like that it alternates between 0 and like 1 or -1, but so lovingly suspected. That's why falling in love instead of planning in love. Yes, Lynn, you're gonna make me like go full on with number theory. I'm gonna regret applying for applied math. I'm gonna try to transfer into pure math. She knew what qualifications he had. Cannot be confirmed what he learned complies with what he would have learned here. Oh, later I'll skip a few steps though. All right. I mean, judging purely based off stereotypes, I feel like the Germans are pretty like rigid with their processes like that too. Math and love are mutually incompatible concepts. That's one take. I feel like a lot of mathematicians have lived out that take too, so I can't even necessarily debate you on that. The idea is that your first n coefficients are 0 in your Taylor series. You can factor... Huh. Oh, okay. Interesting. What is that syntax? Oh, well, that's terrible syntax. Why would you want to do that? Oh, okay. Let's take a look. Classic syntax, like self-torturing with math. Okay, let's see. I see someone posted a question in the Discord too. When was that? Two minutes ago? Well, I'm going to think about the question on screen first, and then... We'll take a look at Blue Ice's question. I used techniques so unfathomably unrigorous, I need to be shot. It yielded a solution that asymptotically satisfied the equation. Okay. How would you solve this? E to the minus D? What is D? The wire stress function? Or just an arbitrary function? D for differential operator. Oh. Oh, it's the big D notation. FizzBuzz apparently likes that. A delay differential equation. This has a name? This isn't a syntax original dish that he's cooked up? Wow. Wait, are we solving for f of x or are we solving for x? I said we need to find an f of x that fits this. So, okay, what's with the integrate by parts? That's worthy of investigation. For me, if someone doing d dx e to the x equals x e to the x minus 1. Is that a true statement? No, that's not true. Okay. There's a generalized method for this. Dickman function? I have to know what that is. That's a funny name. It's like Pikmin, but with more dicks. Oh yeah, I can see a resemblance there. At least his name was Carl Dickman and not Richard Dickman. It is a delayed differential equation, so it's definitely on the right track. So what do I want to... I guess we're going to want to take the derivative of the x. Something's not right. No, I guess something is right. No, something's not right. Aren't they getting a double? Wait. This is the double integral, isn't it? Question mark, question mark, question mark. Method of steps. Yeah, Dick is an abbreviate, or it's like a shortening for Richard. I don't know. There's a lot of weird, um, a lot of weird like shortenings for names. Like William gets shortened to Bill. Don't ask me where the B comes from. Um, what's the long version of Chuck? Charles. But I don't know. From what I've heard, Russian has like the craziest shortenings that have nothing at all to do with the original name. But I think English holds its own too. Sneeds? What's that? Thinking based on the age of the person. No, it's not necessarily an age thing. I mean, some people, like, as a kid, they'll get called the nickname, and then as an adult, they'll choose to, like, introduce themselves as the real name, or as, like, the full name. I think it's becoming less common, though. Oh, it's an old Simpsons joke. Man, I love The Simpsons, but I didn't have Fox growing up as a kid, so I didn't get to watch that many episodes. Sasha is sometimes short for Alexander. Oh, yeah. Um... Shoot, I'm sorry. So this is a... This looks like a discrete delay. A lot of Russian family names being unique to some degree. Oh, okay. The name of an alcohol that sounds kind of like your real name. Um... Oh, yeah. No. Yes? No. I don't know. Uh, I'm gonna put this question on the back burner for now, I think, because I don't know how to proceed. But this is progress. It looks like it's something with the method of steps thing that Jasu also mentioned. But there's a question that I do know how to solve in the Discord that I want to get to. From Blue Ice. I don't understand the first one. I suck at slicing method, but solve a revolution is fine. I'm seeing also there's a differentiate. Okay, that's a quick one. Let me just do that one. Someone in the YouTube chat asked to find the derivative of this. So this is a chain rule followed by, I guess it's two chain rules. You get 2 sine 2x squared times cosine of 2x squared times 4x, and now we just simplify. So 8x sine 2x squared cosine 2x squared. If you're feeling fancy, you could use a double angle formula on the sine cosine, but I don't think it's a reason to. Well, that's why you get the degree first, Jasu, and then you can... And then if they tell you you're not qualified, then they'd be hypocrites for giving you that degree, right? Change my email university name for my PhD because it's a bit too hard to pronounce for the English speaker? Really? Like, I assume it's your last name that's too hard to pronounce? Demand twice your money back? You pay me. The base of a solid is the shape of the region bounded by the graphs of the following equations. Y equals secant x, y equals 3/2. Determine the volume of the solid if the cross-sectional slices that are perpendicular to both the base and the y-axis. Both the base and the y-axis. Okay. Now, they really should have given us a restriction on the domain here. Because the question as it's written, like, infinity, 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 because secant is periodic. Well, actually, not even that. So secant is 1 over cosine. Cosine looks like that, which means 1 over cosine has asymptotes at the zeros and just kind of touches tips with cosine like that. I didn't do a very good job drawing that one. Who cares? Seems not too bad. It's more your first name, which is a long composed French name. Oh, it's not just Sasha? So I assume they're only talking about this piece in the middle. Oh, I guess that is a thing, right? Like, French people have multiple first names that are kind of smashed together. Sasha's more a German/Russian name. Oh, so do you just, like, choose that for your online name? You did? Okay. So this right here is y equals 1. So y equals 3/2 somewhere up here. So I assume they're only asking about this region and not about this region or the next region over or that region. Same with the left side. You guys in the US have a DLC for your name called middle name? Yeah, we do. I don't really know why. There's a neat fun fact where President Harry S. Truman, who was president at the end of World War II, the S in his name is just an S. He, like, his middle name is just the letter S. And that kind of makes me laugh. Like, his parents went through the effort to give him a middle name, but not enough effort to give him an actual name. The names are there so mothers can express grievances. That's true. Yeah. That's a good point. Okay, so these cross-sectional slices are perpendicular to both the base and the y-axis. So they're three-dimensionally... They're like parallel to the x-axis, I guess. You're off now. You need to prepare for a blood moon night in 7 days to die with some peeps. Nice! Good luck with that change. Thanks again for hanging out. Good luck with the 7 days to die. Dreading all that stuff I can't be bothered with, any sorts of bureaucracy. Fair. Marie is a woman's name, but Jean-Marie is a man's name. Don't ask how I know this. No, I mean, I've heard that before. Like, I think like the French especially use like men's names, or like, yeah, like men have names in France that are often what Americans think of as a woman's name. Right? There we go. So we're going to delay differential equation thing. Oh, thank you, BizBuzz, because I don't really know what to do with it besides digging through the Wikipedia page more, hoping for inspiration. So one thing we can do off the bat is notice that this is an even function. So I'm going to only worry about this piece of it and just multiply it by 2. And we should figure out where they intersect. Is this going to be non-unit circle? Oh, this is not unit circle? Dude. Whoever this is, your teacher like hates you. So if secant x is 2/3, that means cosine x is 3/2. Wait. Oh, I reversed it. It's like, that doesn't make sense. It's 3/2, then cosine x is 2/3. That makes more sense. And 2/3 is a horrible thing to take the inverse cosine of. So I'm just going to leave it as arc cosine 2/3. To carry my diploma over to my brother, traveling all the way to Helsinki to show it. You have to physically show your diploma? In America, they just believe you. They never ask for proof. So we're thinking you have multiple first names on your birth certificate? Are they listed separately or as one long first name? Okay, so then for part 1, oh, we might not want to cut this in half. That might be a bad idea to cut this in half. We should not cut this in half. Separately? Wow, that is weird then, yeah. See your diploma from 2017 to make sure it's legit? Huh. Like for like jobs don't ask you to do it. Maybe if you need some kind of like security clearance or something, maybe that they'll ask you. Like if you're doing some super sensitive government job or something. Actually, for schools, you have to send an official transcript, but like it's really easy. Like you just go to your old school's website. They always have some kind of electronic form you can fill out, and they send an email or an actual mail to your new school. So you don't have to do anything else. Making you, actually, for international, that's probably why. That makes more sense. If it's international, that, yeah, okay. Never mind. That does make sense. I forgot. Yeah, you're dealing with cross-country stuff. Old school didn't offer that? Okay. French, they're like Marie Jean Pierre or some random biblical name. Okay. So high school right next to the uni. My friend goes there. I was considering asking her to give me the code to the door so we can during lunchtime to eat for free. That's a neat life hack right there. It's a good song. Um, it's pretty rare in America that high schoolers eat for free. Okay, so we need to. So it's an isosceles right triangle. If the hypotenuse is on the base, then like this width right here is the width of this function, and the triangle sitting on top of it. So the width of the function, since secant is symmetric, it's going to be twice secant x for whatever x value we're plugging in. Because no, I'm sorry, it's just 2x. It's just, wait, am I, dude, the do we need to integrate in y for this, don't we? That's where I'm having trouble. Yeah. Okay, so where I was having issues is that our triangles are changing depending on the y value. So we're going to set up an integral with respect to y. Because the height we're at on the y determines the length of the hypotenuse. So if y equals secant x, then x equals arc secant y? Bruh. And so that gets us this width here. I think that's where I was going wrong. So we're going to do 2 arc secant y. Oh, you know, that means we don't need arc cosine of 2 over 3 anymore, though. Okay, and then this is isosceles. So these are both 45-degree angles, or pi over 4. So we want what we want to get is the area of the triangle. And so it's 1/2 base times height. Actually, you wouldn't even have to worry about the angles. If these are both length A, let's just use the Pythagorean theorem. For arc secant squared y is equal to 2a squared. So a is going to be equal to root 2 yeah, arc secant y. Hey, type 1. And then the area of the triangle is 1/2. The base and the height are both root 2 arc secant y. So 2 arc secant squared. This is a terrible integral to do, isn't it? Zach has 10 integrals left. I hope they take long because I want to rate him before he ends the stream. There's no way we're supposed to integrate arc secant squared, right? I can figure out this problem. Maybe we'll just call it after that. What the fuck am I doing wrong? College problems? Generally, yeah. It's probably gonna be my last problem of the day, though. I'm thinking about this wrong, aren't I? Y is equal to secant x. It's probably going to be secant squared. I'm doing something wrong with the inverse function stuff. The base is secant squared y? Uh, I don't know anymore. I've gotten confused on this question. I want to find the distance from one end of secant to the other end of the secant, depending on my y value. I feel like that is arcsecant when I say it like that. Integral of x squared dy? Well, that's going to be arcsecant then, right? The base of the triangles go on the x-axis, then it should be secant. Well, like, so the hypotenuse of the right triangle, like, this is one hypotenuse right here, and then three-dimensionally, the legs go up in the air. But that's a terrible integral to do, isn't it, Fembox? You don't have to evaluate it, just set up the integral. Oh! Well, that makes life easier. Okay, well, if we don't have to... Okay, then I feel better about this. Oh, is it like a calculator allowed problem? I think the work I was doing was right. I just thought it must be wrong. I was assuming you have to do this by hand, and that's not a. If it is possible to do that by hand, it's not easy. So yeah, I think this length here is 2 arcsecant of y. And then through the process I just showed with the Pythagorean theorem, get 4 arcsecant squared y equals 2a squared. So a is 2 arcsecant y root 2. Yeah, root 2. And so that means the area of one of those bad boys, 1/2 times a squared. So the integral that I would set up here is arcsecant y squared dy, and then y ranges from 1, the intersection point down there, to 3/2. So yeah, if you wanted to actually do that integral, I have no idea how the hell you would. But if all you need to do is set it up and like plug it into a calculator or something, then that's great. Is that true, syntax error? Is she the one who's going to give out the $1 million? So yeah, red ice or blue ice on Discord. I'm not explaining this well because I wasn't very confident in what I was doing. But it really helps to draw just one of those cross sections and figure out what that has to look like in terms of your variables. And this is a pretty annoying example to have to do it with. Like, this is not an easy question for this type of question. So the first thing to realize is that you need to integrate in y because we're ranging from one y value to the other. And it's not going to work if you try to do it with x. you saw where I got stuck on that. And then, so you want everything in terms of y, so you have to rearrange that equation. And you just have to know that, or you don't necessarily have to know, but like arcsecant is going to be this thing reflected across y equals x. But you have to cut it in half because because like that violates the vertical line rule. So I guess you would take the upper half normally. And so I think that's why we needed to multiply it by 2, because we cut it in half. My bad professor is known for making simple concepts extremely hard. I'm sorry to hear that. You know, I should I'm not the only one who does this. On YouTube, there's a friend of mine named Dr. Gold who does math help also. He can do these types of questions as well as me in case I'm not around. On Twitch, there's a lot of people who do this. We have 2 hours. Okay. But yeah, that's how we do it for part 1. He's just throwing some difficult functions at you to work with. Oh no. Syntax error. If you're listening, FizzBuzz posted an answer. Hey, Switzerland. All of Switzerland is watching? Wow. Hello. For part 2 with equilateral triangles, we can reuse some of our work from here. Because we already know the base is 2 arcsecant y, so that means the other 2 sides are the exact same. And then in equilateral triangle, all these angles are 60 degrees. So we can cut this in half like that to get the area. Oh, it's the thing. IVP, trig integral, trig sub, PFD. Wire stress. I haven't heard of wire stress for integrals. I'm sure his name will be on there somewhere, though. We might just know by different names. The class average was a 36. That sucks. Pythagoras theorem on curved surface? No, I can't. Sorry, Somnath. This remaining side by Pythagorean theorem will be... It should be root 3. Yeah, it is. Okay, so then the area of the original triangle is 2 times the area of that triangle. So it'll be 2 times 1/2 base times height of that. Arc secant y times root 3 arc secant y. So now just clean that up. We'll get root 3 times arc secant squared y. So that's kind of cool. It's going to be the exact same integral, but you stick a root 3 in front. Okay, and then semicircles. Here a cross section looks like that. The entire width is 2 arcsecant y. So the radius is half of that, just arcsecant y. So the area of an entire circle is pi r squared. The area of a semicircle is half of that, so 1/2 times pi. And then the radius we said is arcsecant. But we're squaring it. So the integral, wow, it's kind of, these integrals are all the same thing, just multiplied by a constant. That's kind of weird. Arc cosine 1 over y. Well, I'm pretty sure it's an identity that arc secant y is equal to arc cosine 1 over y. I think it's the same thing. Okay, yeah, Fenlux is saying the same. So it should get you the same answer. And thank you, FizzBuzz, for digging more into syntax errors question. So yeah, Red Eyes, I hope that helps. Let me know if you have any questions. Let me check up on Zach's stream. What number is he at? $93. Okay, good. The Devil's Staircase? I'd never seen that one before. Okay, we have a bit of time before Zach ends. Just delaying a bit. Did you post your asymptotic solution? I didn't see it. Oh, oh, that was, never mind, I did see it. That was your E to the thing. I definitely wouldn't be able to explain that. So yeah, I feel bad cutting off that conversation, but I guess it could continue in Zach's chat. I doubt he would mind. Because I kind of want to go over and support him, so I think we're calling it here. I haven't seen anything else from Red Ice either, so... Are you a graduate student? I'm about to start on a master's, Orange. So yeah, people who are here on YouTube, thanks for being here. I'll be back on YouTube on Saturday. But yeah, Orange, Red Ice, Somnath. See y'all later.